All right, so in this lecture we're going to be continuing our series on vulnerability exploitation by talking about the heap overflow. So the heap is simply the area of memory where dynamically allocated variables and data is stored. The heap itself is controlled by a heap manager, and similar to the stack where there was information like the frame pointer, base pointer was stored, return address, and when we wanted to exploit the stack, we tried to manipulate that data, that maintenance information. There's similar but different types of metadata that's used by the heap manager to control allocations and manage the free store. And it's that data that, for heap exploitation that we're going to want to try to corrupt or manipulate to achieve, whatever the objective is. So heap implementations themselves vary from system to system. And so this makes heap exploits very much system specific. And in this lecture, we're going to be talking about mostly techniques that apply to Windows XP, Service Pack 1, and earlier. Starting with Service Pack 2, and certainly in newer versions of Windows like Windows 7 and Windows 8, there are a number of different protections that have been implemented that make heap exploitation more difficult. Not impossible, but makes it just harder. And so these same concepts that we'll be talking about here still apply and are important to know. But for if you're running a newer version of Windows like Windows 7, some of these techniques, and you have a new application on that platform and you want to try to some of these techniques against it, you may encounter some difficulties because of these additional protections. And so my recommendation would be to, if you wanted to try an experiment with some basic heap exploitation, would be to set up a virtual machine with an earlier version of XP, and then kind of using that just to kind of learn the basics before trying to do more complicated exploitation for newer platforms. All right, so most of you are probably familiar with these functions. These are your standard C lib routines for allocating memory, resizing, reallocating, and freeing. When you call malloc, it's not actually making a call to the operating system every single time to give you the memory. Malloc implementations are they want to be fast, so as quickly as possible give you the memory that you requested, but also try to reduce what's called fragmentation. We'll talk a little bit about that. And so there's different routines for these allocators, and they have different algorithms for how they maintain the free list. And what's important to know is how, for the system that you're targeting, it's important to understand how the allocator works in order to craft a reliable exploit. So let's take a look at what does a proper allocation look like. So here's this very simple program where it takes an argument, and we're computing the size of the argument, mallocing or dynamically allocating enough memory to hold the size of that argument, and then we're copying it into the buff. Now in general, it's a bad idea to use stir copy, but in this case, we're computing the correct size, and it's being copied in, and then we're printing out what was the buff variable, and then after that we free it. And so as you can see down below, when we run this simple program, we can pass it various variable sized parameters, and it's going to print them out. If we want to look at some incorrect uses of memory allocation and some of the mem copy or string copying type functions, here's several examples taken from the Shellcoder's Handbook, which is a great book, by the way, especially like if you're wanting to get serious about some of the different exploitation techniques that we're talking about. This is a great reference to have. There's also many good articles online if you want to look at more examples and more detailed walkthroughs. I'd highly encourage that. But if you just look at some of these, you can see in many cases we have memory operations like the first one here There's some integers that we control, a buffer we control, and we can influence the destination. And so with that, you can do quite a bit. Likewise, on the like the login down below, there you see it. It's allocating a fixed size buffer, but then it's stir copying in a user supply buffer. And so, of course, if we control that, that could be of any size. You can then overflow that. So under Linux, there's a couple different implementations. You have Douglas, malloc, which you can go online and read more detail about that. But essentially, you have unallocated memory that's grouped into these different bins. And each bin just has a linked list of blocks that are of similar sizes. So this makes it quick. If somebody says, okay, I want a 16-byte chunk of memory, that it can go to the bin for 16-byte chunks and return a pointer to that memory. There, if you look at Wolfram Golger's malloc, PT malloc, and then what was incorporated into the glibcs, they also incorporated, it's kind of based off of Douglas malloc, but incorporated something called fast bins and some other things that get you a little bit more of a performance benefit. So here's an example, just to see some of the, what I mentioned earlier, this metadata or maintenance information that you see in the heap. This shows on the left here, you can see what an allocated chunk looks like. And it's going to have the size and status field, the user data space for where the actual data is that you have. And then if you look at what a free chunk looks like, you have a doubly linked list. Here we have a pointer to the next chunk in the bin, and then as well as a pointer to the previous chunk. You have your space for whatever the size is, and then a size. And so what this does is this makes it easy by having this size parameter and the pointers. It makes it easy to coalesce these into a larger. So if you have two chunks, one freed and then another one comes and becomes free that's adjacent, it makes it very simple to coalesce these and to have a larger chunk. And doing that is what reduces memory fragmentation. On the right, you can see just a kind of a visual illustration of the bins. And so if you want to read more about DL malloc, there's a web address at the bottom of the screen where you can go to, and that will talk in a little bit more detail about this. So I mentioned fast bins. So this is very similar to the DL malloc. Fast bins basically means that once you've freed a block, rather than it doesn't try to coalesce at all. So if somebody requests that same size, it can immediately give it back to them very quickly. So it's great for speed, but you have to, of course, worry about balancing fragmentation. And so, because if you have too many small pieces, if somebody requests a size that doesn't meet that, then you're going to have these gaps where the chunks, you have areas of memory that aren't usable because they haven't been coalesced or joined back together. In Windows, we have there's private heaps, and there's also what's called like the default heap, and so every process has the default heap. But you can also create. There's a series of functions you see here: heap, create, destroy, etc. that you can use to create these additional private heaps. And so we had talked in a previous lecture about, or at least introduced, the process environment block. One of the fields that's in the PEB is you have a pointer to the default heap, and then you also have a list where you can point to your other heaps that may be in the process, as well as a count variable for the number. At the bottom of the screen here is a link that tells you a lot more about the Windows heap and some of the exploitation that we're going to cover in this lecture. But if you want to go into a little bit more depth, I would recommend going to that, visiting that site. All right, so the Windows heap, it's allocated in 8-byte chunks. And these are called allocation units or indices. A set of these allocated chunks is going to be called a block. So As an example, let's suppose somebody's requested 18 bytes, then your block size is going to be 24, right? Because it's going to be in multiples of 8. 16 wouldn't be enough, and so the next multiple up would be 24, and so you have 24 byte block. And these blocks have headers, which have some of the metadata describing the block. So if we drill down into what's in these block headers, we have the size, the segment index, so the actual memory segment for that block, unused, so how much free space. A busy block is going to be one that's allocated or in use, whereas a free block is one that obviously is not in use. And the free block has the pointers, they're called flink and blink. Blink is going to point to the previous chunk, so it's actually pointing back to the previous chunk's flink pointer, and then flink points to the next chunk. The free list, excuse me, is basically an array of 128 doubly linked lists, and you can see how it's basically called the free list. And these are the flink and blink pointers that we talked about on the last slide. On the free list, the index 0 is actually variable size, and so this is going to be blocks that are larger than 127 chunks, but also less than 512K. And so they're going to be sorted actually from smallest to largest. And then it kind of goes up from there on the indices. Windows also has this notion of a look-aside list. And so this is where if you've freed a block, it gets recorded into a singly linked list on this look-aside list. There's 128 singly linked lists. And so blocks are added to this look-aside list whenever free is called, but there can only be up to four in this list. So at some point, your look-aside list can be filled, and then that's when they're going to go back to the doubly linked free list. And so this kind of builds up what I was saying previously. So each look-aside list can only hold the 4 blocks, and then if this fills up, then they're going to be restored to the free list next. So here's a visual illustration that shows the two, both the doubly linked free list and then the singly linked look-aside list. And you can see where the flink and blink pointers point to. And you look at the beginning, your blink is going to be pointing to the last entry's flink pointer. And the last entry's flink pointer is going to be pointing to the beginning flink pointer. So these are important to understand in the upcoming slides. When we talk about what we want to overflow and overwrite, understanding how these pointers work becomes important. I also include on this slide here there's another link for that talks about defeating Windows XP Service Pack 2 heap protection, and so it's another good reference to take a look at and explore this in a little bit more depth. All right, so we're going to run through both how the allocate algorithm works, and we'll get into freeing and coalescing on the next slides. So this is a bit of an eye chart, but essentially, if you have a size greater than 512K, then this will be in virtual memory. It's going to be used for this. If it's less than 1K, then first look-side lists are going to be checked. If there's no free entries on the look-side list, then check the matching free list. Okay. If it's greater than 1K, no matching is found, then we're going to use the heap cache. We're not really going to be talking much about that in this lecture. It's greater than 1K and no free entry in the heap cache, then it's going to be using the initial free list. That was the variable sized free list that I pointed out in the previous few slides. And at the end, if free entry can't be found, then the heap itself is going to be extended. And again, reference the presentation at the bottom in this web link that we'll talk a little bit more depth about some of these algorithms. So the free algorithm, here we're going to look to see, is the chunk less than 512K? If so, then it's going to get returned to either the look-aside or free list. And again, this is going to be dependent upon whether there's space in that look-aside list. The chunk's less than 1K, put on look-aside, but again, can only hold the 4 entries. So if that's full, it's going to go on the free list. If it's greater than 1K, put on the heap cache or that variable sized first index of the free list. All right, so that's allocation and freeing. Coalescing, which I mentioned earlier, this is when you have 2 adjacent memory blocks are freed, and then we're going to combine these to have, you know, a larger block. And so the main reason to do this is to reduce fragmentation, but it has a bit of a performance impact because you have an extra step taking place here. So one thing to note is that on the look-aside list, there's no coalescing whatsoever that's taking place. But only when these blocks are going to the free list will coalescing possibly happen. So this just kind of outlines the free to look-aside algorithm. The buffer is free to the look-aside list only if it's available, so present unlocked. Requested size is less than 1K, so it fits in the table. And the look-aside is not full, so there's not more than 3 entries. And adding to the look-aside is very simple. Just simply insert it into the appropriate singly linked list. And the buffer flags, remember on the previous diagram we had a busy as well as a free. These will be set to busy, and that, having it set to busy is what prevents coalescing from taking place. All right, so what I just ran through relatively quickly was the basic allocation algorithms and freeing algorithms for how Windows works. As we shift now into talking about exploitation, one of the things that is important for a reliable heap exploit is that knowing the state of the heap before you actually throw your exploit, or getting it in a state that to where things are predictable, and that's important is to be predictable. And so there's 2 different schools of thought. In one case, you could do an extensive amount of reverse engineering to be absolutely certain of how the state of everything in the heap is at that point in time when you throw your exploit. The other approach is to try to get to make a set of calls or perform functions that will get the heap in a state that you want it to be and that you can kind of predict how it will be. And so heap spraying is one of these techniques. And the idea is that you're quote spraying a lot of information on the heap so that the position of your allocated object is going to be predictable. And this is really popular in browser exploitation, especially with like JavaScript. So if you look at this little diagram here, you see before the heap spray, it says all this free space, and then after the heap spray, we have all these nice little chunks of allocated space. So it's predictable now where the next allocation is going to be because we've filled it up with similar size blocks. And so the idea behind heap spraying is that, okay, if we get in a state where we can predict, and then we're going to put a lot of these no-op shellcode pairs onto the target heap. So the idea is that if we don't know exactly where our code is, or our target is, but we know in general it should be within a given range, well, if we've blasted a ton of no-op shellcode there, then you can know that, okay, if I jump into this range, then there's a good chance of landing on that no-op. It's called a NOP sled. And so here's the code below. You can kind of see an example of building up the NOP slide and shellcode and malloc. So here we're essentially creating a megabyte string of no-ops followed by the shellcode. And then we're going to fill 200 megabytes of memory with copies of this NOP slide and shellcode. So it's quite a bit of memory we're taking up, but it's going to make exploitation more reliable to do it this way. So another example of heap spraying is, suppose that you can overwrite a C++ object. Well, we can point into the heap, perform our heap spray, and then wait for the virtual function call. So if you recall back to a few lectures back when we were talking about how vtables are laid out, and you look at this diagram here, you can kind of get a sense of how that might work. So we've overwritten the C++ object, right? We've overwritten the vtable, and the address is going to be getting us into the range where our NOP slide and shellcode is. And so just think about this intuitively for a second. In the code sequence you see here, you have we're getting the vtable address, passing the this pointer as the first argument, and then now it's calling an offset, in this case +8, into the vtable, and then this is going to take us into where our code is. So basically we've just completely overwritten this object, and once that virtual function gets called, then it's going to take us in, hit our NOP slide, and then we've got execution with our shellcode. So that's one example of something you can do. Another technique is called Heap, Feng, Shui. And so these are, again, techniques that manipulate the heap layout. Often this is dependent upon the size of blocks, so one technique is called the plunger technique, and here we're just allocating and then freeing 6 really large blocks, and then the goal here is to clear out the heap cache. Another technique is defragmenting it. So so we're going to allocate blocks that are the size of our exploit, and the idea is that all of the holes are going to be filled, and the new blocks are going to be allocated from the end of the heap. And again, now that we know it's going to be allocated from the end of the heap, then this gives us something that we can predict. So to read a little bit more in depth about this topic, there's a link at the bottom here that talks about, this is from the Black Hat conference a few years back, where there's a lot of different techniques that are discussed. So if we take a step back and think for a moment about, well, if we're going to do this heap overflow, what do we actually want to target? What are we ultimately trying to do? Well, ultimately, we're trying to control some pointers or some globally allocated data. So some of the pointers that are common targets are things like the global offset table, which has functions that we can call different function pointers. Vtables is earlier illustration gave. In the process environment block, the PEB, there's a function pointer, and again, we'll talk about that in a few coming up here. Unhandled exception filter, it's a very common one. So we're going to talk about a few of these in the next few slides. But the main idea is that we want to overwrite this heap maintenance information, right? So this metadata is in the heap, and then we want to, if there's a call coming up where free is made, well, some of the behavior for the heap manager, if we've corrupted the pointers, then that can give us the ability to overwrite information. And if what we want to overwrite are some of these pointers or these types of pointers, so that we can then have the pointer point to our code, and then that's how we're going to get execution. All right, so the first thing we're going to talk about is this coalesceonfree 4-byte overwrite. So when we say a 4-byte overwrite, what this means is that we can write an arbitrary 32-bit value to an arbitrary 32-bit address, right? So that's 4-byte. There's also, it's called a 4 to n byte overwrite, and this is where we use a 4-byte overwrite to be able to then subsequently have an arbitrary n bytes of information that we've overwritten. All right, so here's an example. The diagram here shows where we have an allocated block and followed by a free block and then some free space. and you can see where our overflow data is in our block, and we've blasted over all the heap metadata, the size, previous size, flink and blink, etc. And so what we've done in this case, we've overwritten these 2 pointers. Okay. So we've overwritten the flink and blink, and if that block that we overflowed is coalesce, right? Again, we're talking about behavior that is heap implementation specific, right? So on Windows XP in particular, when the blocks are coalesced, you have this code that runs. And in this code, so EAX, this is pointing to flink, ECX is pointing to blink. So think about this for a second, what's actually happening here. We have the flink, whatever value is in flink, is being written to memory pointed to by ECX blink. But then the value that's in blink is being written to the address pointed to by flink +4. So first, just think about conceptually how this is working in the normal case, right? You're running coalesce a block, so you need to update the flink and blink pointers, and that's exactly what this is doing. From an exploitation perspective, this is giving us an arbitrary 32-bit overwrite because we control flink and blink. Now, one thing to note is that both of these addresses need to be writable, right? Otherwise, it's going to trigger an access violation. But you can actually use this to your advantage by having, the blink point to a writable address, and you overwrite your flink, and then the next one. If flink is not writable, then that's going to create an access violation. Well, if what you've overwritten is for example, the unhandled exception filter, then that could actually work to your favor because now you're using this specific behavior to trigger an exception, which is going to then call into your exception handler routine. So this is, like I said, this is again, specific systems. This is great for systems before XP Service Pack 2. Things get a little different on later systems, but there's similar things that are taking place in those later systems. So this general concept is basically the same on other systems. All right. So that's the coalescing case. Another case here is a look-aside list head overwrite. So this is going to be a 4 to n byte overwrite, and what we're going to do is we want to overwrite look-aside list head, right? Okay, then so we're going to allocate that head, and have the allocated chunk points to the value of our overwrite. And so the idea here is that now we can overwrite whatever we want, and it's essentially like having access to raw mallet calls. All right, so drilling down into this in a little bit more detail, and again, you can reference the link at the bottom for a little bit more detail, because this slide in particular gets to be a little, it's pretty detailed. So we're going to use the coalesceonfree overwrite technique that we talked about earlier, and we're going to overwrite blink and flink as is described here. Okay. And so blink is going to point to the address of the look-aside table for the chunk size. And we want chunk size to be an infrequently allocated size because we want to be at the beginning of it, right? We want it to be at the very beginning. Flink is just going to be a pointer to whatever we want it to point to, which is going to be, of course, our code. And so to calculate that blink value, you can use the formula that you see here. Now, these specific numbers, again, this is the heap place plus the hex 688 value. That's going to be the first entry, and that's because there's other, like the linked list and whatnot, that are going to be immediately after the heap base. Index, that's self-explanatory because again, remember the chunks are 8 bytes in size, so this is just calculating where the index is going to be. And then entry size, is hex 30, so the simple calculation then results in your blink there. And then these are the values that you'd put for the rest of the metadata. All right. So I mentioned earlier about potentially targeting the unhandled exception filter. And so the goal in this case is that we ultimately want to install our own, so that if we trigger an access violation, then at that point, since we've installed our own, then that's how we're going to gain execution. And the UEF is sort of the last ditch. So after vectored exception handling, after frame handling, all of those, at the very end is the unhandled exception filter. So like most of the things we're talking about in this lecture, the location of this is going to be OS and service pack dependent. But if you want to find the location, you can disassemble the set unhandled exception filter function. And so here we have the code for that, and you can see the UEF is pointed to the address on your screen, 77ED73B4. Okay, so that's the location of it. Now, the way this works is that when the UEF is called, EDI, so right before it's called, EDI is pushed on the stack, and EDI contains a pointer to the exception pointer structure on the stack. Well, it just so happens that hex 78 bytes past EDI, there's a pointer to the end of our buffer, which is, of course, we could use that to make the start of our own shellcode. So the game plan here then is that we want to use our arbitrary 32-bit overwrite, like we talked about before, to patch the UEF address to point to an instruction that's basically calling EDI plus 78, which may seem like, well, where are you going to find that? Well, there's actually a few places where this particular instruction is found. And so on XP, there's a number of DLLs here, and so that's what. So by having it point to that, it's going to call EDI, the structure, plus 78, which is going to redirect execution then to the end of our buffer. So exceptions triggered, address of it's going to get called as this instruction, and then that call, because EDI is points to this structure, it's going to wind up getting down to our code. All right, so we can also exploit vectored exception handler. Now, we talked in the previous lecture in the Stack Overflows about frame-based exception, or structured exception handling. Vectored exception handler this was introduced in Windows XP, and all the vectored exception handling information is actually on the heap, so this works perfectly great for our heap overflows. The other thing about vectored exception handler is that these get called before any of the frame-based handlers like SCH. And so the pointer to the first node happens to be at a hard-coded address, and so our goal is going to be to overwrite this pointer. All right, so the vectored exception node is going to be stored in the heap. You can see at the bottom of your screen here what that structure actually looks like. You have a pointer to the previous node, next node, and then you have a pointer to the handler. And so on Windows XP, SP2, the address you see here, the 77FC3210, this is a pointer to the first vectored exception node. So to do this exploit, the idea is that we want to create our own handling structure, and then fix that first VH pointer, the one that's hard-coded, to point to our struct. Okay, and then we'll find a pointer to our buffer on the stack, and then set the first pointer to be that buff pointer -8, right? And that way we'll get to call the handler. All right, so another target to exploit is the process environment block, so the PEB. The PEB begins to store in the heap, and every process has one PB is modifiable. Okay, and so there's a couple of function pointers that are in the PEB. XP in earlier systems, the address is predictable, so this is a nice, reliable means of exploitation. Not so much in we'll have that point to the instruction that executes the back of our home buffer. All right, so we can also so the first TB is going to has a base address you see here, and it's growing downward. So in between with each additional thread, it basically allocates a hex 1,000 bytes space, so going down towards 0. And so when a thread exits, then the new thread gets assigned the old thread's TB address. But the problem with this is that this makes it more unreliable, because you don't really, unless you have a very good understanding of when these threads are going to be exiting and where they'll be, it makes it harder to predict where the TB is. But if the address is predictable, then of course you have reliable. And so this is especially nice for single-threaded programs, right? You don't have to really worry. You know exactly it's going to be predictable because you just have one thread. And just like the other case for the actual exploit, we're going to be replacing the pointer with an address to the instruction that's going to execute from our buffer. So you should be seeing a kind of a repeating theme here. We're targeting function pointers, and we're having these different potential targets, and these targets are targets. The only reason why they're targets is because they hold function pointers, and some of them are in predictable locations, and so that's why that kind of makes it a prime target. All right, so now we've kind of talked about, well, how do you actually do the exploit? One of the things that's also very important is fixing up the heap. So as you might imagine, if you're overwriting some of this heap metadata, there's a really good chance that you're going to get a crash, an access violation. I mean, almost guaranteed, in fact, if you don't do anything to repair it. And so if you want to create a stable exploit, this is an important step. And so there's these two different approaches. If you take a lot of time to reverse engineer and understand exactly how the heap should be, you can get it into that. That can be the state that you fix it up to be in. But a more generic and easier method is just to make it look like a brand new heap. So, and you can do that just by fixing up the pointers in the tables, depending on what you've overwritten. You can make it so that new allocations occur after your block, and then the program should work just fine. Because, like I said, new allocations are possible. And so the technique, if you look up, if you go to Google and you search for the ASM-repair-heap code, you'll see there's actually a nice listing of assembly code that will fix up the heap for you. And so if you read through that and study that, you can kind of see exactly how to do this. And this should be the first thing that your code does when you get execution, is you want to fix up that heap and then continue on and perform whatever tasks that you need to. So one last thing to note is when you're doing this reverse engineering for your heap, having a method to visualize the heap and see, visually where data is going is important capability. And so the OllyDebug Heap Viz plugin is one tool that I wanted to point out for this. But any debugger, WinDebug, OllyDebug, IdaPro. I mean, it's up. Take your pick. You can use those to explore the heap, but if you can find plugins or tools that help visualize that can actually make your life a lot easier. And so it's just something to check out. Right, so that concludes this lecture. Again, if any questions, send us an email. And like I said before, I would highly recommend it's one thing to kind of understand conceptually how to do the heap exploitation, but to really fully understand it, it's good to do this and practice on your own. And so if you reference a book like the Shellcoder's Handbook or any number of articles online, you can kind of see a more detailed example. And so maybe take an older program or take something where there should be vulnerable, or create a simple program yourself that's vulnerable, and give it a try. Just look at how the heap is set up and structured, and then see if you can go through and gain execution by using one of these techniques. So, all right, and then that concludes the lecture. So thanks a lot.